In this lesson, we will discuss ring homomorphisms. So just as we had homomorphisms between groups, we will now define homomorphisms between two rings. So these ring homomorphisms are maps from one ring to another that preserves the additive and multiplicative structures. So let's begin with our definitions. We're going to let R and S be rings. Then, first definition, a ring homomorphism is a map phi from ring R to S that preserves the two ring operations. So that is, for all A, B in the ring R, we have phi of A plus B equals phi of A plus phi of B. So in particular, this makes phi a group homomorphism on additive groups. So if we view R and S as additive groups, we still have a regular group homomorphism, as we studied before. But further, we have phi of A times B equals phi of A times phi of B. So now to check that a map is a ring homomorphism, you have to check that it preserves addition and multiplication. Secondly, a bijective ring homomorphism let's say phi from R to S is called a ring isomorphism. And we write R is isomorphic to S. So from the context, if we're dealing with rings R and S, then R being isomorphic to S means they're isomorphic as rings. Thirdly, let's talk about the kernel of a ring homomorphism. This is actually the same as the kernel when regarding phi as a group homomorphism. So the kernel of the ring homomorphism phi, denoted KER phi, is the set of all elements in R that map to 0 in S. So map to the additive identity in S. So again, this is the same as the kernel of phi as a homomorphism of additive groups. So this is the same kernel as we studied in group theory. So just as we used homomorphisms to study group structures, we're going to use homomorphisms to study the structure of rings. So let's look at an example of a ring homomorphism. Let's define the map phi from the integers to the set of integers mod n for any integer n. We're going to define phi by phi of a is just mapped to its natural coset a plus nz. So we're mapping a to a mod n, basically. So this is a ring homomorphism because, well, let's look at the additively. We know phi of a plus b would be a plus b plus the ideal nz. But then this can be written as a plus nz plus the coset b plus nz. And this is phi of a plus phi of b. So this map preserves additive structure, and likewise it preserves multiplicative structure, because phi of a times b would be a times b plus nz. And as we define multiplication of cosets, this equals a plus nz times b plus nz, or phi of a times phi of b. So we have phi is a ring homomorphism, and this is a very common homomorphism that just maps every integer to its residue mod n. So this projection map, this natural projection map, of the integers onto the ring of integers mod n is called reduction mod n. So every integer is just mapped to its residue mod n. And when considering the kernel of this homomorphism, we see that the kernel would be the integers that are mapped to the 0 coset, but that would be any integer that's a multiple of n, and therefore the kernel is the ideal nz. This next example, let's look at a homomorphism from the set of polynomials with rational coefficients to the ring of rational numbers. So we're going to define this map. We're going to define it by phi of a polynomial equals p of 0. So this map takes a polynomial and maps it to its constant term. So this map is a ring homomorphism. So note that phi of p of x plus q of x, well, the sum of two polynomials can be written as the polynomial p plus q of x. So phi maps the polynomial p plus q of x to p plus q of 0, and this is equal to p of 0 plus q of 0, which gives us phi of p of x plus phi of q of x. And phi of p of x times q of x Similarly, it can be written as phi of p times q of x, which would be mapped to p times q of 0, which equals p of 0 times q of 0, and that is phi of p of x times phi of q of x. So we see that phi is indeed a ring homomorphism. Let's look at the kernel of phi. So kernel of phi would be the set of polynomials that get mapped to 0. So this would be a polynomial whose constant term equals 0, but any polynomial whose constant term is 0 must be a multiple of x. So this is the set of all multiples of x in the ring. But we write this as the ideal generated by x. So we see that the kernel of this homomorphism is the ideal generated by x, or all polynomials with a 0 constant term. Next, we're going to prove some properties of ring homomorphisms. So I'm going to let R and S be rings. And I'm going to let phi be a homomorphism from R to S. We're going to prove 3 facts. First, we want to prove that if A is a subring of R, then the image of A is a subring of S. So then phi of A, which by definition is the set of all phi of little a, where little a is an element of the subring A, then this is a subring of S. So we see that a subring gets mapped to a subring under a ring homomorphism. Secondly, now in particular, if A is an ideal, then it's not necessarily true that phi of A is also an ideal. We need one more condition. So if A is an ideal and phi is onto, then we can conclude that phi of A, the image of A, is an ideal of S. So we see that if the ring homomorphism is onto, then it maps ideals to ideals. The third fact we're going to prove is that the kernel of phi is an ideal of R. So let's begin with the proof of property 1. Now A is a subring and is therefore non-empty. So since A is non-empty, we see that phi of A will also be non-empty. Now let's take two arbitrary elements of phi of A and show that phi of A is closed under subtraction and multiplication. So if S1 and S2 are elements of phi of A. So these are elements of the ring S. Then we know that S1 must equal phi of R1, and S2 equals phi of R2. For some R1, R2 in the subring A. Then when I subtract S1 and S2, so then S1 minus S2 will equal phi of R1 minus phi of R2, which is phi of R1 minus R2 by properties of homomorphisms, and therefore this is in phi of A. Since A is a subring, we know that R1 minus R2 is also in A, and so this is an element of the image of A. And similarly, for multiplication, S1 times S2 would equal phi of R1 times phi of R2, but again, by definition of a homomorphism, this equals phi of R1 times R2, and since A is a subring, R1 times R2 is still an A, so there's an element of phi of A. So we see that phi of A is closed under subtraction and multiplication, and therefore we see that phi of A is a subring. Now for the proof of property 2, we know by property 1 that phi of A is a subring of S. So again, we're assuming that A is now an ideal of R. So it remains to show that phi of A is closed under arbitrary multiplication in S, and that will show that phi of A is actually an ideal. So it remains to show that phi of A is closed under arbitrary multiplication in S. That will show that phi of A is an ideal. So let's let phi of A, little a, be an element of phi of capital A. And let's take an arbitrary element of the ring S. And we need to look at the multiplication of phi of A and S and show that this is in phi of A. Well, now here we're going to use the fact that phi is onto. So since phi is onto, and S is an element of the codomain, then there exists an element R in the ring R such that phi maps R to the element S. Now let's look at the multiplication S times phi of A. So S can be written as phi of R, and phi of R times phi of A will equal phi of R times A, but this has to be an element of phi of A because R times A is an A since A is an ideal of R. So we see that the multiplication S times phi of A is in phi of A, but likewise phi of A times S equals phi of A times phi of R, which is phi of A times R. And again, A times R is in the ideal A, so this is an element of phi of A. So we see that phi of A is closed under arbitrary multiplication, and this follows since A is an ideal, therefore phi of A is an ideal of S. Now we're going to show the third property, that the kernel of phi is an ideal. Now we've proved in group theory that any group homomorphism always maps 0 to 0, that is the identity of R to the identity of S. So since phi of 0 equals 0, we know that the kernel of phi is not empty. And we're going to show that kernel of phi is closed under subtraction and arbitrary multiplication in R. Well, if A and B are in the kernel of phi, then by definition we know that phi maps A and maps B to 0. So then phi of A equals phi of B equals 0. Let's look at phi of A minus B. Well, by properties of homomorphisms, this is phi of A minus phi of B, which equals 0 minus 0, which is 0. So we see that the kernel of phi is closed under subtraction. Now let's let R be an arbitrary element of the ring R. And again, let's let A be in the kernel of phi. So we need to show that the product RA and AR are both contained in the kernel of phi. Well, phi of RA will equal phi of R times phi of A, which equals phi of R times 0, which will be 0. So we see that R of A is in the kernel of phi. But likewise, if I just do the multiplication in reverse order, AR will be in kernel of phi. So we see that kernel of phi is not empty, it's closed under subtraction and under arbitrary multiplication in the ring, and that shows that the kernel of phi is an ideal. So we just showed that the kernel of a ring homomorphism is an ideal. It turns out that any ideal can be identified as the kernel of a homomorphism. So we see that ideals and kernels of ring homomorphisms are synonymous. So if I is any ideal of ring R, then the map phi from R to the factor ring R mod I defined by phi of R equals the coset R plus I. This is an onto ring homomorphism with the kernel of phi equal to I. And this homomorphism is called the natural projection of R onto R mod I. So the proof, we know that R mod I is a ring, and the map phi is a group homomorphism with kernel I. So we need to show that phi is a ring homomorphism as well. Well, we just need to show the multiplicative property of this homomorphism, but this just follows from the definition of multiplication of cosets in R mod I. This follows from the definition of multiplication in the factor ring R mod I. So we have phi of Rs would be equal to Rs plus I, which is R plus I times S plus I, and that is phi of R times phi of S. So we see that this is also a ring homomorphism, and the kernel is still I. So next we'll look at an isomorphism theorem for rings, and all of the isomorphism theorems for groups have counterparts, have corresponding theorems in ring theory. And so the proofs of these various isomorphism theorems consist of using the theorem from group theory to obtain an isomorphism from one additive group to the other, but then you take that isomorphism and check that this group isomorphism is multiplicative and is therefore a ring isomorphism, kind of just like we did in the last proof. So we're not going to present all of the corresponding isomorphism theorems for rings. We'll only present the first isomorphism theorem now. So if phi is a ring homomorphism from R to S, then R mod the kernel of phi is isomorphic as a ring to the image of phi, phi of R. So again, the proof is basically identical to the proof in group theory, so we're going to omit the proof. But here is an example of the first isomorphism theorem that I've actually claimed already. So let the ring R in this theorem be the ring of polynomials with integer coefficients, and we're going to define a homomorphism to the ring S, which is going to be the set of integers. So let's define phi by phi of polynomial p of x equals p of 0. So this map is a homomorphism. We actually demonstrated this when the coefficients were rational numbers. So the same work would show that phi is a homomorphism of these two rings. But phi is also onto since for any integer n is also in the ring of polynomials with integer coefficients, and phi of n would map to itself. So we think of a constant as a polynomial in x as well. So since phi of n equals n, we see that phi is onto. So that is the image of the ring equals all of the integers. Now the kernel of phi is the set of polynomials such that p of 0 equals 0. And we saw earlier this is the same as the multiples of x, and so this is equal to the ideal generated by x. So by the first isomorphism theorem, for rings, we see that the ring of polynomials with integer coefficients mod the kernel of phi, so that's mod the ideal generated by x, will be isomorphic as rings to the image of phi, which is the ring of integers. And recall we used this earlier when we showed that the ideal generated by x is prime, because when we take the factor ring, it's isomorphic to an integral domain. So I've just proved my claim that I used earlier that this factor ring is isomorphic to the ring of integers.